Well, hello and welcome back to Old School Coding. This is continuing the session from earlier today where I started putting together the simulation of the VoidStar 8080 system. So just to recap for everybody, we are building a microcomputer simulation, a signal precise quantized simulation of a 1990-ish microcomputer using C99, which is substantially identical to the language that I was programming in the late 80s and early 90s, and using the development techniques in vogue at the time, at least with me and the people that I worked with. So back to it, we were just setting up this simulation module that looks like a VoidStar 8080 system as described in the BIOS that we are putting together. So, as with all other modules, I've gone ahead and hooked up all the signals. It was just boilerplate work, so I did that before turning the stream back on. It looks something like this. It's where we have our module that we're initializing. We got a whole bunch of submodules we initialize, and down here we pick out all of the various signals that have to be linked between them. So for instance, phi2 comes from the clock generator and has to go to the CPU, yada yada. All this is just slam it together. Don't have a paper tape punch reader yet. And here's where we hook up our, well, these guys, this hooks up our ports for our various character devices. And this hooks up the ports for the block device controller. RAM first, then ROM. The test that I took this from did the ROMs first. It didn't matter there. It matters for us because we're going to have RAM for the full 64K and then replace the top 2K with the ROM chip. So we need to hook up the ROM afterwards. We have a seek function, so when we do a seek, we start doing reads and writes to the BDEV controller. We will get a seek call that says, here's where to find the data. And that's all in the BDEV model, so it's all set up. We just needed to write the seek function. And then more boilerplate as we tell everybody that they've been linked up, and then we call everybody's invariants to make sure we're cool. Down here, this is the link up that means that we now see these things. Let me see if I can turn them on. Yes, how about that? So the yellow background is my printing console, and I've made it roughly the same color as the paper I used to use in my teletype. The green on black is a green screen video display, 16 lines by 64 columns, which is going to match a lot of microcomputers of the day. And they're dead in the middle in nice pastel green. That's the line printer. Now, I wish I could have my background alternate so that we'd have 3 lines of green background and 3 lines of white background. But managing to keep the green bar stuff proper while moving content around and having the background go all the way to the end of the line, even though we weren't printing characters there, is a bit of a pain. So I'm just going to do that with green. Well, for right now, our boot ROM only really deals with the TTY. So we can turn those off. So when our boot ROM comes up, it should print something there. But we're not going to be printing anything quite yet. Because while I hooked everything up, I didn't yet put in anything to initialize disk images or ROM images or anything. So let's do that. So over here, I'm going to look in my hex directory. And it strikes me that I did a whole bunch of renaming without fixing these up. So excuse me really quick while I fix that. So we're going to remove the old files Let's trigger a build again. There we go. Now, one of my pieces of assembly code has an error. I think it's AXA. This is actually a copy of a file from another document, AXG. Yeah, basically this is the sector blocking and deblocking algorithms. It's full of macros and such, and I didn't really finish working on it. Not important because we're not using it, and it's kind of a good idea to leave the error there until I get in and actually fix it. So what we have here, we have our boot ROM, which is actually under VoidStar 8080 ROM.lst. There it is. And this defines what the ROM is going to look like. It is assembled to start in the highest 2K of memory. And it takes up not a whole lot of it, which is good because I want to put in a ROM monitor, which means I need to add code to that for commands. Currently, all this does is accepts a command line and then says, I don't know what to do, and then says, I didn't recognize this command, then goes back to prompting you for a new line. But it does do input and output, which we would see on the TTY if we loaded it up. So I am going to start looking at my argument vector. I'll do that. So basically, as we recognize parameters, I will continue in the loop. Unrecognized R VoidStar 8080, which means that our first parameter we're getting is the name of the system. So we need to start with 1. And I'm going to start building things on my command line to do this. So VoidStar 8080, and I want to read void rom equals VoidStar 8080 underscore ROM. So that's what I want to put on the command line. So we need to recognize ROM equals whatever. Oops, too few arguments to str and compare. Str and compare of ROM equals argp and 4. So that compares those two strings, but stopping after 4 characters. So this says to do, load VoidStar 8080 underscore ROM to ROM. So what I'm going to do here is ROM load of argp plus 4. Now this guy is going to need to have a hook into the ROM, and I'm just going to pass it right here. This is going to be a VoidStar 8080. We're going to start putting this new stuff down at the bottom. And I goofed somewhere. So it's finding an error here. An expansion of stub. What the heck? Oh, right. It's always something really stupid when it puzzles me like that. So, to do, VoidStar 8080, please load this to ROM. So what I'm going to do is now write cstr path. We're going to try to load the bin file first. Is that what I want to do? So this says, this guy is an image for the ROM, which starts at ROM base. Now there actually is a hex loader that I have built in. Let's maybe use that. There we go. ROM 8316 load. And we go to sys arrow ROM sub 0. And the base address is OXF800, which is our boot ROM location. And the file is format of hex/%s.hex. Like that. What did I mess up? I messed up a parenthesis. Okay, no idea if that worked. So what we're going to do is after we load it, I'm going to do a ROM dump real quick. Because we have that available. I know because I've got a test that does it. So it's ROM 8316 underscore dump. Like that. Oh. See, I get to moving quickly and I forget to actually read the error messages. And here is what is now inside the ROM. You see that we're just barely tucking in. This means that we can add quite a lot of in the way here of commands. I'm thinking things like dump address ranges and set memory and jump to things. But does it match our listing? So what we should see is F3, C3, O4, F8. That looks good. So I believe that we have got the right data into our ROM. So now if I actually ran it, we should work. So how am I going to run the system till a designated end condition? Well, I think what I will do is run it until we have a halt instruction. Because the only way out from a halt is an interrupt or a reset, neither one of which we're going to be generating from here. And the best way to do this is to go ahead and look at the test code for the i8080 and see what it does. So it has this thing for one instruction here. Well, a halt instruction is not going to stop because halt, we're not going to get red M1 going. So what I want to do is look at how we're coming out of reset. So reset for testing. Looks like this. And we're going to call this static void reset to halt. So this will be responsible for starting us in the reset mode, starting us in reset, and bring us out of reset, and then simply running until the halt acknowledge is set. So who is testing halt? HLT is in here. And this is not terminating when it detects a halt because it might not if it's got a bug, but it will provide us with a plot. And the plot should be EID.HLT. So here's what it looks like when we do a halt. You notice that the wait signal goes high and stays high. I thought there was a halt acknowledge here. That is probably a bit that is set during sync that nobody is decoding and printing here. Hold on. So, what is the footprint, the fingerprint of us going into halt? We're actually sending a status halt ACK here. I may need to go into my controller and have it latch the halt signal. Lower sync, try data, Yeah, we actually will want that to appear on the screen. If we build a front panel, we'd want lights lit up. In fact, we would want them for all of the status bits. So we have a request for a feature. We go down to the 8228, which is decoding it. So currently what the 8228 does is it sees the data. Start reads. Latch the status here. Okay, so if I start mucking with this, if I start grabbing all 8 of the status bits and putting them out on wires, that's going to happen every M1 cycle. So what I'm going to do instead is I'm going to allow other people to look at the status word inside the latch. It won't have a callback, but that's okay. Now the status bits are here in I-8080 status. And it's HLTA. We're going to wait for HLTA to go high. Reset to halt, defined but not used. So now, I can turn off the ROM dump. Now I'm going to do one thing more. Once I see HLTA, I'm going to run for another 45 tau, another 5 t-states worth, to give us a run out. So if we were collecting trace information, we would see it. We're not going to, because this is just going to run flat out here. But if we were, it would be there. Now I need a verbose flag. So standard, well, custom in Unix systems is dash, char, is a bunch of single character flags do things, and dash dash word is a word flag that does something to set an option. So we're going to say if argp sub 0 is equal to dash. We're just going to scan RP across it. We're going to say stub to do parse flag option %C. Now, as we see these options here, I'm not going to stop the execution. I suppose we can go to the next argument here. If we get into this, we had a bunch of flag words, so we want to continue here. Yes, I'm using my own code here to parse arguments rather than pulling in a big library to do it. I know that. this is on purpose. There's another school of thought that says you can also do this with a minus sign. With a plus sign. So you could say plus V and minus V. I'm not so sure about the leading plus character as a flag. I always worry that my shell may be doing regular expression parsing. So I like to use lowercase and uppercase to be increment and decrement. So this gives me a verbosity flag that starts out at 0, and I can move it up and down. Then I could say here if verbose is greater than 1. So we'd need to do -VV to get this guy out. So if I said -VV, oops, it would print it. Oh, and we should now be actually doing something. So I'm looking over at the printing terminal, and let's turn that on. What's happening on the printing terminal is we are getting just a really rapid, lots of new lines being printed. And I betcha it's scrolled all the way off. Yeah, so I can't see what the beginning of that looked like. But that does mean that my TTY output is hooked up. And it means we're actually, oh, and that's output being produced by the simulated CPU running a bunch of assembly code that I just kind of blasted out last night without even thinking. So we're alive. We need debugging, but we're alive. I'm going to leave this TTY mapped up here, so as we do things, we'll just do it. So in the options, I'm going to want a couple more things. I want to do a dry run. Actually, D is debug, N is dry run. And now we can down here we can say, before we do it, so we could say if dry run is less than 1. So any positive value of dry run will skip that. So now I can turn off the VV, and I can even put -N there. To do, parse option flag N. And if you start it too soon, it's going to say, no, go away. So -N says dry run it. The other flag I like to have along with verbose and dry run is debug. Now, because we're parsing all of our parameters in order one at a time, we can turn on a debug flag and then load up a disk or something and then turn it off again. We could also have a specific argument that says, at this time, run until halt, or at this time, run until some condition. But we're good because we are printing stuff. Let's take a look at our source code now. Now we start to do the real engineering of the time, which is actually working in assembly code. So VoidStar 8080 ROM. So we are resetting the disk controller, setting the stack pointer, and we are printing that. I'm suspecting what's happening is that TTY-ILM, which is my inline message code, the idea there is that you print each byte. When you get to a 0, you return to the byte after it. So I'm suspecting this is printing its first byte over and over again. So we pop our return address, so HL now points at the string, and we call TTY-STR. When we get back, we're going to return to the byte after the 0. And indeed, I forgot an INX HL. So now if I do this without the -n flag, look at what it printed. I can type stuff in. Hello world. And nothing happens. Okay. Let's take a look. So TTY-ILM did get into it. It did print out the prompt. Here. So then it called getLine, which starts a pointer at a keyboard buffer. In fact, let's look at LST. And I am going to move this over to the, oops. Get the right window. We're going to sacrifice the upper left-hand corner so that our TTY can be seen. Just like that. Okay, so let's read the code. It's too bad I don't have a front panel. I could see what addresses it was spending its time in. But we do know that this TTY-ILM thing here does work, and we can use that construct elsewhere for debugging. So we called getLine. HL, so HL points at our keyboard buffer, and we're going to clear it. We're going to keep 0 and increment until INR sets the 0 flag. Let's make sure. I've had problems before where I forgot what flags were set. So inkdeck INR. So does INRL actually set the flag? ALU is temp +1. So we are indeed setting the flags. So what I'm going to do here So, and you'll notice what's on the port there is that we did not get to printing the message that says KB buff cleared. So I am suspecting that INR is not setting the Z bit.
Yeah, don't stand by the back foot.
And I have to redo this twice. First time I do this, it's just too fast to reconnect. So you notice what's going on here. We are clearing KB buff byte over and over and over and over. What this means is that INR is not properly clearing the Z flag. Now I think I know what's going on here. I think we are handling an ALU flag to DEC flags, which is 8 bits, but it's actually more than 8 bits and it has 256 in it. So we just found a bug in the INR instruction. Let's fix that. So Z is ALU amper OXFF. So this means that this particular subtest is now failing because move L 0xFF, INRL was not setting the Z flag before, it is setting it now. So I apparently didn't think through all of the cases properly. So this should now be not 1.6, but 5.6, because it's Z, AC, and P. There's the Z flag. So there are probably other places where we are testing that. This one also is an increment from FF, so this should be a 5.6. Okay, and now we get this KB buff cleared down here. And I've got my text buffer, and I have my backspaces working. Now that's actually explicitly handled in the monitor code. You have to recognize the backspace, you have to send backspace, space, backspace, and you have to zero out the value in your keyboard buffer. And if I hit return there, it does that, and we're good. So the other thing I want to do before I finalize this is XPDF of DCM doc 880 microcomputers. Let me verify absolutely positively that I am correct on what INR should be doing before I call this a fix. Hold on. PDF viewer, where are you? Where did PDF viewer go? There it is. Drag that onto the screen. So we're looking for the definition of the INR instruction. I skipped over it somewhere. INR. INR register. All condition flags except carry are affected. Okay, so let's double check that we're not affecting carry. So we need to make sure that the value that we're sending here in old, right, we're doing the right thing. So old is the previous flags. We grab the carry flag from old and we carry it through and set it here. So carry flag is still correct. All the other flags are being set. So that's good. Oh, come on. So the ASM file is here. We need to get rid of
Don't stand
these
behind
debug
her.
things.
And don't stand by the back leg. You'll get kicked.
And notice that I messed that up in the editor after I checked it. Okay, so now we are back to this. Testing, return, bar baz, and Control U. Control U is erase entire line. I've decided that along with Control U canceling the entire line, I'm going to then enter a blank line so that we get a fresh prompt on a fresh line, just in case there's detritus on the screen. Now, the other thing that I'm testing is if the input is too long, it should stop and beep at me. And I believe our limit is 255 characters. Okay, it's beeping at me, but it's continuing to add X's. Which means I'm printing the X before I'm deciding it's bad. So we go back into ASM. So go down here, get line backspace. Oh, this is our little loop. It's the only real significant piece of engineering in this file. Basically, start with a keyboard buffer that I'm going to page align. So it's aligned on a 256 byte boundary. So I can increment and decrement the L register, and if it goes to 0, if the L register goes to 0, then I'm either decrementing off the front or incrementing off the back. This means that offset 1 into the buffer is the actual first character. So this clears it. Then we say here is the first character of the return. We're going to put the HL, we're going to put the address of the string we input into HL, so our caller doesn't need to know where keyboard buff is. And then we're going to take the first character and suck it into A so that the caller can just look at it directly. We call TTY get. End of line, we have cancel and we have backspace. If it's a control character, we're saying nope. So I should be able to go in here and say Control X. Don't know if that's coming through or not, but that is reading in the bell. Probably isn't. I think I have system sounds turned off going into OBS. So otherwise, add to buffer. Hey, we wrapped cancel. So if we did do this, I need to also put out those 3 characters. So we're kind of pretending that teletypes could erase content. Typically what systems did, and I first saw this on a Unix system in '74 about, is if you were on a printing console and used the delete character, instead of backspacing the head and then over getting that, what it would do is it put a slash, and then as you delete a character, so if you say A, B, C, and then hit backspace 3 times, it would have ABC slash CBA, and then we start typing in and put another slash in. So you'd have between slashes the part that was deleted. Kind of clever. Another thing that I thought would be cool, and I don't know how to do, I don't know how to do it efficiently in 8080 machine code without doing a lot of work, is you type ABC and you hit a backspace and you overstrike the C, and then you move out to where you have an overstrike. And you get another backspace, you go back and you overstrike the B and you go back and so on. That would require some fancy dancing in the buffer to keep track of which characters on the display were overstriked. So when you go back to overstrike the next one to delete, you get to the right one. So I'm just going to say TTY is going to be a glass TTY. And that should have set that anyway. So inserting those lines should make it so that we can see our maximum line length, stop our mouse cursor from moving. Now we will get the X being added and removed over and over and over again. And it would be unfortunate if each time it did that, it caused the screen to scroll. So see there, it's not going any shorter. And if I hit Control U, of course, Control U isn't going to go back across the whole thing. If I were to make this terminal exceedingly wide, I don't know if that's wide enough. There we go. Now Control U should erase all the way back through all the X's, and there we go. So at this point we can start adding commands to the monitor. I think what I will add is a command that does a boot from a disk. I think that's just going to be B. So if we start with a B, we're going to do a boot. Let's make it really simple. Do I have a... Okay, so we are resetting the BDEV controller. We don't have any code in this file yet to do anything with the disk. However, come on. I have worked on a cold boot. The original ROM actually just started off by moving from disk into memory. Is cold my stuff, or no? This is the stock cold start loader. Okay, so we're going to have to implement this from scratch. So I'm going to do a couple of things. I'm thinking that we'll have a boot from drive A, and later we'll have a separate boot from drive B. So dispatch to a service function. Okay, so what are we doing here? LXI. We're going to push HL. So we're going to save the address of our command. TTY ILM overwrites all of that, though. Oh boy, which means when we call dispatch, I really want to have a little better control. So get line, call dispatch. So we're going to document HL points to the command line. A already has the first character from the line. We're going to ignore the fact that TTY ILM is about to destroy the accumulator. I will refetch from H. Okay, so now I have something at A that I want to compare with a bunch of entries. So LXI HL command table. We need a table scan loop that basically says compare M with the accumulator. BZ found it. If not, we XHL 3 times, since the command table is going to have the command byte, the character, followed by an address. How am I going to know if we got to the end? Let's put the command in C. Now, compare, let's see, if A is 0, I believe I can find out if it's 0 by doing an OR AA. Let's make absolutely sure. So if I do an OR A with itself, it will clear carry and AC, but it does set the other flags. And if it's non-zero, T-scan. So we get here if it's not found. If we get here, then we found the command in C. And we can now say inks HL mov L mov E comma M inks HL mov D comma M, so low and high bytes. Exchange yeah, if I exchange that, will put my command address in HL. PCHL will then branch to that, and when that command returns, it'll return to whoever called dispatch, which is what we want to do. Now if we run it, there'll be no commands. Well, it won't compile because we don't have a command table yet. And I'm going to have the Sentinel be 3 bytes just because I like the idea of keeping my table right. And command table len, actually, EQU dot dollar minus command table over 3. So now, instead of using the Sentinel, I could do basically based on size. That's probably better. Yeah. The A command be boot A for now. B boot B, C is boot C, D is boot D, yada, yada, yada. X is execute at address, L is load, S is store, yada, yada. We'll figure it out. This is all going to be very dynamic. So now, instead of this, I've got command table. I can leave my first character in A. I can now do a compare of M. BZ found it. I can then do a DCR of E. I can do a JZ of not found. Inks, inks, inks. Jump T-scan. Or equivalently, there we go. So we compare, found goes down below. So we go back down to here. Now if I say XYZ, it should do a command not found. Okay. So there, dispatch ... Command is followed by grabbing the character and putting it, and then putting out a new line and grabbing the character again, and now scanning the table. Compare M, BZ found it, ink, 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 decrement E, jump on non-zero back to scan. Command not recognized. So the reason why that didn't change is because I used a opcode BZ on line 220. because I actually spent most of my career at that point when I was working with the 8080, I was using Z80 opcodes. And other CPUs I used also used B for branch. Usually the difference was that a J had an absolute address and B was relative. So you often used the B mode, the B opcode. Things like this where it's close together, you just want to branch down a few bytes. It would be shorter, especially on a 32-bit CPU. Which explains why nothing happened when I tried to run it. So we've accepted the connection. We say foo. It should be printing something. Push HL. The other thing is that I'm going to return to the command table here. So this would be jumping off into the weeds if we ever got here anyway. Let's work through this. Push HL, pop, move C push, call, pop, move, push, searches, call TTY-ILM command not found, or found at either one. So after I do this exchange, I'm going to pop this into DE. And actually, XTHL will say whatever's in HL, swap with the top of the stack. So exchange puts my destination address in HL. This puts the destination address on the stack and puts the saved then we return. There is our dispatch function. So get line, let's make sure we're doing we're not going to put a new line there because dispatch does that for us. Come back from dispatch, we're going to do the same thing again. And in this case, there. This does not need to maintain HL. So if I say hello, it's printing nothing. are we actually getting the new ROM image? Yes, we are. So what I want to do here So I'm going to put a build key in there, which I can bump from time to time to verify that I'm getting new versions of it. So, yes, interesting. When I hit return, it's going all the way back to warm. That is interesting. And on first entry, I just got back garbage. Ah. Oh, I'm Gakumba. Helps if you got a stack, huh? So just for fun, just in case something is going wonky with this, I'm going to start my stack in low memory this time. There's the problem. So we don't actually have memory where I was putting my stack. So RAM boards, we got 4 RAM boards here. We're initializing them there. For each board, we're doing that. Just going to print the name of the read signal. And for ROM, like that. So here's our initialization. We get all of these hookups to RAM. We get this final hookup to ROM at F8. Okay, so that did what I wanted. Again, this is with the stack pointer set to 100 hex. Dispatch done, looping back to Mon. So I want to put some test code in here. I am going to report memory size somehow. So we're going to check at the beginning of each kilobyte. We're going to write the inverse, and read it back and see if it changed. And if it didn't change, then we have the number. So MVI, I'm going to put C is 0. Actually, I can just LXI HL. And I will print out the test address that fails. Actually, I think there's a complement accumulator I can use, CMA. Is that right? Or am I thinking of somebody else? CMA, complement accumulator. Yep, we can do that. So if ROM is found, then I want to inks. Actually, I want to do INR L BNE memcheck. INR H BNE memcheck. This is because INX, I don't believe, sets any flags at all. I'm going to check that. It'd be nice if INX set the carry flag or the 0 flag or something. INX, no condition flags are affected. If we get to here, let's call TTY ILM DB 1013. So HL now has the base address of something that is not RAM. In a real system, there is the possibility that I would write a byte that would go nowhere. It would turn around and read a byte from nowhere, and the data that I wrote would still be on the bus. On the simulated system, I don't believe I have that problem because on 8080 at least, between the two, you've got a sync pulse. So if that gets driven out onto the data bus, that's going to change the contents. So ROM found. So I want to print a bunch of characters. So first of all, push HL. And we have mov a comma h. I am going to print this in octal, I think. No. If I want to print the number of kilobytes, yeah, mov a comma h, SRA, I believe. Not through the carry, so it's not RAR. You could tell it has been a while since I have done math on an 8080. So we've got rotate left and right. Oh, RRC is rotate left and right. RAL and RAR is rotate through carry. So I want an RRC. I want to rotate this right by 2. So if the number of kilobytes is now in the A register. Don't make me divide by 10. I don't want to divide by 10. Well, I've got 6 bits left. Let's do it in octal. Okay, so I'm going to put a character that is the next 3 bits. We're going to put a 0 first. Push BC, VIC, comma 0. I have no idea if that's going to work or not. RAM as far as the eye can see. So apparently, We're not decoding any ROM anywhere at all. Oh, that's bad. I'm going to put a question mark out for each character that I check because I am not absolutely confident we are actually executing that loop. We are not actually executing that loop. What the frippin' do? Well, first of all, it would help if I didn't use BNE. Yeah, so my compilation here is not including error messages from the assembler. And 116. This is an MVI into C. And 156 is a RET. And now we are assembling without errors. So we're printing out a whole bunch of question marks that looks like about 256 of them. Which means that when we are writing to the ROM space, we are getting back the value. Fudge. Tossing it asleep into the command line so I don't have to keep rerunning this twice to get each one going. What if I let this fall down into here? It should say 00, 0. Yep. Okay, so we are actually falling through the bottom properly, and we would be printing 00 KB octal. Oh, bloody hell. This is loader checking every byte, which means that something has gone wrong with the decode. Okay, I'm going to tell the decoder to drop the writes completely, but this still should be using the ROM at that ROM chip. So from 0, less than ROM chips, plus chip. ROM chips is 1. We have 1 ROM chip. I'm not going to print where I mapped at the RAM. I think what I'm going to do now is I'm going to reduce RAM boards to 3 so they don't overlap. Trust me on this one. Below minus 2 times 1024, ROM chip read name. Still RAM as far as the eye can see. Make sure we're getting build 2. There's build 2, still RAM as far as the eye can see, and we are seeing a decode pointing to the ROM read here. We should not be seeing RAM at any of those addresses, which makes me wonder what dispatch is doing. I think what I'm going to do is instead of complementing the accumulator, I'm going to say INRA of AM, save it in C, increment it, write it to M. Move C back into the accumulator, compare it with M, jump non-zero to ROM found. Going to be pissed if it's Gen Z that's doing the wrong thing. Oh, wait a minute. That's right. That's reversed. I'm not getting any RAM. Oh, wait a minute. I think shadow is still active. There we have it. I think it's shadow. I think what's happened is, first of all, okay, read the original value, save it for comparison, write different value, compare original versus memory if unchanged, this is not RAM. Okay, so the difference is here, what's happening is we're not actually writing to anywhere. We're not reading back anything from RAM. We're not actually be able to load it. So this says 0 kilobytes of memory detected. So this right away said, oh, that's not memory. Now, what am I doing here? I'm setting the board, I'm setting the chip, calling decoder linked. Where does decoder initialize those pointers? Right here. So once we've written them, they should be there. What I'm going to do is I am going to repeat these loops down below. very bottom, yeah. So those are linked. This all passed. Let's not worry about checking the rights. So the other thing is this is probably a shadow problem. So in the decoder, do we ever see releasing shadow? We never see releasing shadow. Oh my goodness. So ROM base, disable, jump warm. So disable interrupts, jump to F804. This trigger at F8 should have caused decoder.c to do this. So we see our test triggering it. Not releasing shadow, FF. Okay, this is a known weirdness during reset where we can get a memory cycle. I thought I fixed that though. I was sure I fixed that because this cycle, no, that's correct. This isn't part of our run. I am going to put in a start-end pair here where we're doing the run. So we're starting the run. We're running the code, but we're not actually branching. Okay. Well, goodness. So why is this not doing it? I mean, this first jump here, jump warm, should get here, and it should be executing out of high memory. Wait a minute. Oh, I'm stupid. There are two places where we check this logic. We check it on memr fall and on memr rise. Yep. And we do see indeed that we are releasing shadow during memr fall. So I'm thinking is memr rise doesn't even need to check this. There. So we are releasing shadow. So now the question becomes, why are we not seeing any memory accesses? I mean, literally, no memory detected. Foo. Dispatch command is garbage. Haha. So we are actually not seeing memory responding. Okay, confirm 10 bits for the page offset, 16 bits for the total address. So there's the total pages. So if I set that to 4, we won't have to worry about null pointers for now. So here we go. Here's our decodes. All these guys are going to 8080 RAM 2, RAM 3, RAM 4. And we're getting a segmentation fault here. Oh, right. So let's have the ROMs not set that to null, so that we can at least see what was behind us. Orderly. Okay, that's what I expected. Although I just thought I just turned off the null. So despite shadow being reset, we're not actually seeing it. I'm really not seeing why our RAM isn't being activated. Okay. We are correctly seeing this. So we are modifying the read signals for the last two kilobytes of RAM to point to the ROM. We've released shadow. Oh no. What the hell did that come from? Okay, there it is. Thump. Thump. This basically says anytime we are accessing the ROM, we turn on shadow. Where did that come from? This comes from source I80, let's see, test. So I grabbed enable shadow from here. This basically is saying that the shadow signal, no, that's correct. Okay, so when are we calling? That's correct, okay, I'm good. So when we call enable shadow, it's setting shadow to point to our ROM. That's correct. And what I was thinking of was we're using that to do the thing. So this says assert. So if reset rises, we're going to enable shadow. Over here, interesting that it's not printing it from what we call it here. Because I haven't compiled. Okay, I'm starting to make silly mistakes. It's probably time to wrap this up. I was hoping to get this working, but it's not. So what I'm going to do is I'm going to spend some time debugging this on my own and not on camera, see if I can figure out why we are not able to read the memory. We should be able to write a value at 0 and read it back and get the data. We have tests that do this. Why is it not working this time? So we're going to call it a stream. And until I can come back with that debugging done, try to keep it small and safe and fast. Oh, and try for correct, maybe. We'll see. See you then.